So you will spend like half of the time on it. Yeah, I will have a brief introduction about our guest speaker here, Dr. Ying. Dr. Mark Ying, he's also Whitney Professor of Mechanical Engineering at the University of Pennsylvania. He currently leads the Responsible Innovation Initiative at the School of Engineering and Applied Science, examining ethical and socially conscious technology development with over 3 decades of pioneering work in modular robotics. His research group has created systems from humanoid showcased at the Philadelphia Museum of Art to the world's smallest self-powered flying robot. His interest also spans product design, robotic performance art, novel locomotion, and steerable needles, with application in urban search, rescue, and healthcare. Before joining UPenn, Mark spent a decade in industry, and he earned his PhD from Stanford. Without further ado, Mark, the floor is yours.
Thank you.
Thank you.
Thanks. I don't know how many of you do this, but that was my ChatGPT summary of my bio. One of the things in that is the responsible innovation effort, which is new. So the dean a couple months ago said, this is an important thing that we need to do for the school, and he wants me to lead that effort. Unfortunately, he doesn't know what it is. I don't know what it is. So I'm trying to figure that out, and hopefully you'll help me figure out what that is. And that's going to be the second part of the talk. So the Prometheus problem is basically, Prometheus was, he stole fire from the gods. This is Greek mythology. He gave it to humankind, and that technology, the gods didn't like, Zeus didn't like that. And so he chained him to a rock, and then there was a bird that pecks at his liver all the time as his punishment. And so Prometheus represents technology and progress, but also the responsibility that comes with technology and the consequences. So the problem is basically...
Possible, there's a OK there. It's broke some of the...
Oh, yeah, sorry.
Yeah. Okay, we're good. Thank you.
Sorry about that. Just see. Okay, yeah, sorry, there's a chat on random thing on Zoom. So what is the Prometheus problem? Essentially, how can we ensure that the technologies that we develop as scientists and engineers can be used in a good way? It's the bad way. There's always a good side and a bad side to different things. The positive potential, you make some kind of cure for some disease, or you develop some improvement to the quality of life. On the other side, if we have some high-tech cameras or something that's really great for a variety of things, flying drones, but they can also be used for surveillance, or there are bad sides to autonomous weapons, environmental damage, or things that we do that can be negative. And so there's often the weighting, how do we evaluate the good versus the bad? And that's essentially what we're thinking about with the Prometheus problem. So essentially the talk I'm going to give today is split into 2 parts. I'm going to talk about modular reconfigurable robots. This is what I've been doing for 3 decades. So I'll talk about that, and then in the context of robotics, you can look. I want to spend a little bit of time about responsible innovation and think about how could robotics relate to this Prometheus problem. And also, hopefully, we can have an interactive discussion with you, just to think about what is responsible innovation, how should we think about things in terms of helping scientists and engineers in education in universities as we develop things to do things responsibly. So with robotics, what could go wrong? I don't know if many of you have seen this. This is Terminator 2, the T-1000 robot. How many people have not seen this movie? Just a couple. Wow. Okay. Usually it's young students that I've seen. Oh, they haven't seen this movie because it's too old. It's from 1991. But if you haven't seen it, essentially, it's the Terminator movies. It's a robot. In this case, it's the liquid metal robot evil, kills people, bad, can't stop them, you can't kill them. That's the type of thing. So, what could go wrong with robotics? This is like the classic example. And in fact, when we talk about modular robotics, people say, oh, modular robotics is the first step to this kind of liquid metal robot. So what is modular robots? Essentially, modular robots are robots that are made up of repeated modules that you put together into larger forms. And there's essentially 3 or 4 different types of architectures that we can classify them. And there's what I call the chain type. So you have modules that you put together into chains, articulated chains. And then there's a lattice type where the modules form into a larger lattice and can form structures. And then there's something we call the hybrid, which it reconfigures using the lattice shape, but it can form articulated arms and things like that. So let me just show you some more examples of what each one of those are. So this is just videos. These are all from Xerox PARC before I went to Penn. So this is 25 years ago. So these are all different robots that we called polybot that you can put together and that can do things like climb stairs, different forms of locomotion. The middle one is a video that's showing manipulation. Of course, we had a Xerox box on there. It was good to put the Xerox logo in our demos. The one over here shows that you don't need to actually be in a humanoid shape to use human equipment. The one over here is, this was the largest number of modules that we had in a single system, which is, I think it was 45, maybe 35 modules, something like that. So we can have lots of modules that you attach together, rigidly attached, and you can do a lot of different types of things with them. That's the chain style. This is the lattice style reconfigurable robot. So this is what was called DARPA. This is a DARPA sponsored project that was called TEMP. The idea is this is a scale model of ISO containers. So large 20-foot containers that if they were out in the ocean, they would jump off the boat and then drive around, and you can form large floating platforms like an airfield, or in this particular case, a bridge that spans from one side of a land to another side, and you could drive cars across it or something like that. So that's forming different shapes in 2D. This is actually what's called telecube. The idea here is that you have modules that form lattices, but each module is essentially a cube that has the faces that can expand out and attach to other modules. And then in this case, you can form again shapes by having them expand and shrink as they move around. So the lattice style system is good at forming shapes, but not necessarily doing things. The chain style is much better at forming arms. If you have arms, you can do articulated things. You can put objects, push on objects, manipulate objects, and that type of thing. So in general, but the chain style tended to be more difficult to reconfigure. So the hybrid one is kind of both. You can reconfigure more easily using the lattice style configurations, and then form arms or whatever you want to do some useful things. Okay, so what can you do with these? There's so 25 years, a quarter century ago, before some of you were born, we wrote a paper where I said there are the 3 promises of modular robotics. They can be versatile because you can change their shape to adapt to whatever task you need to do. They can be robust because if one of the modules fails, you can reconfigure. It's redundant, so you can throw away that module and you can keep going. It can be low cost because you have repeated modules. If you have lots of repeated modules, you can use economies of scale, and the cost of the modules go down. At that time, the modular robotics self-reconfigurable research group was growing. There were more and more people. 10 years later, Casper Stoy said this at one of the workshops we had. In reality, these things, they don't do anything useful. They break all the time, and they're very expensive. So basically, the first one, it's true. They don't currently. We haven't done anything useful with them. You don't see them anywhere doing anything useful. But I still think it's versatile in the sense that we've shown hundreds of different types of tasks we can do. So it's versatile. It's just not necessarily useful. versatility. They break all the time. Yeah, it's an experimental system, so that's kind of common. But at the same time, we have lots of modules, and you have a lot of modules, probably greater chance that one of them will be broken. We just have not really pushed on the self-repair aspect. So if someone really pushed on the self-repair, maybe they could be more robust. I just don't know about that. They are definitely more expensive. And I think systemically, they just will be suboptimal because you have that versatility. There's a cost to that versatility, and you can't be necessarily optimal, at least in terms of expense. Okay, so one of the main things about, when we think about the Prometheus problem is the value versus the cost of things. And so what is the value? The value from these systems primarily comes from versatility, I believe, and that's like the main thing that's different. You can form different shapes. So it can form different shapes, so you can split into multiple pieces if you want. If you have 10 modules, you can split into 10 different robots that could go around and do 10 things at the same time. Or you could form one larger one. If you need a longer reach, you could do that. So it can do lots of different things, but the cost of that is that the 10 little ones will be less capable than the one big one. There's always a cost to all of these different things as you split up. There's a tendency for people to think about having more modules as being more interesting. If you have more modules, there's more you could do. The combinations that you can put them into grows exponentially. So that adds more versatility. But the cost of having more modules is that you have more failures, you have more pieces that can break, it's higher cost, and it's less optimal. Actually, so I want to take one step back real quick. How many people here are more interested in modular robotics than responsible innovation? Just raise your hand. Let's see. Okay, how many people here are more interested in responsible innovation than in modular robotics? Okay, all right. So it's about half and half. I had thought that, this being an engineering talk, that it would be more on the modular robotics, so I'll try to be a little bit faster on the modular robotics side to leave more time for responsible innovation. Okay, so there's, what I'd like to do is talk about 3 different issues with modular robotics. The first one is size and the number of modules. So there is a tendency in the community that's been around for a while, shrinking the modules, making smaller and smaller modules. Maybe people are thinking about the T1000. Let's see if we can get to that molecule size liquid metal robot. Essentially, if you have smaller modules for human size, let's say you have a task that's human scale, then the smaller the module, the more modules it will have that will do that task. And so then it can be more versatile. If you have more modules, you have more CPUs, you have more sensors, more degrees of freedom. And each module is smaller, takes up less material, so at lower cost. There's economies of scale that can come into play. On the other side, making things smaller is hard. It's harder. Every time you make things smaller, it's going to be the smaller CPU, the smaller sensors. Usually they're not as good if they're smaller. The total system cost, even if each individual cost is smaller, is what you really won't want to worry about. If you have $1 module, that's great, but if you need 1 million of them, it's cost you $1 million. So the total system cost is the important thing. And sometimes economies of scale doesn't actually scale faster than the total system cost. So just to give you an idea, I want to stress the difficulty in miniaturization. So I've designed my group has designed a bunch of different systems. I don't remember exactly, many dozens. And all the time, the thing that we struggle most with is squeezing things into the design. The miniaturization is the hardest part. So we want to give you some examples of those. Here are some of the lattice-style robots. This is, while I was at Xerox PARC, what we call Proteo. We designed a system that had these prismatic joints on the inside. Essentially, the idea is that you have modules that are rhombic dodecahedrons, which is a space-filling geometry that could roll around the edges, that could dock to each other on the faces and roll around each edge, and this is one way to do it. The problem was it was about this big, 20 centimeters, and it cost about $20,000 per module. We did not make these. They were too big, too expensive. Telecube is another one. We had a DARPA contract that we did build. These were about $1,000 per piece. There were 6 centimeters on the side. This is the one that I showed a video of where the faces expand. This is what's called digital clay. So it's a rhombus dodecahedrons, and it had a CPU and sensors on the inside, but there was no actuator. So you could form a shape with your hands or whatever you want, external actuation, and it can recognize what shape it's in. Essentially, the cost of shrinking down is loss of functionality. And it's just hard. At the time, putting actuators into something that was 1 centimeter was really hard. And theoretically, you could do something like shape memory alloys, but even then, getting it to work in the useful ways is difficult. And the chain style, these are some of the other ones. This is probably about G1 before, generation 1. This is generation 3. They're about 4 centimeters on the side. This is a system that we call ratchet, and very similar to the previous one. There's no internal actuation. You actually had a motor on the outside that would move them around, and you could form shapes. It's a dodecahedron. No, these were right-angle tetrahedrons, which are also space-filling. So the interesting thing here, just an interesting design aspect for these polygon modules. This one was our first generation. It was just a hobby servo with some electronics on it. It cost about $100. This one was our high-end system that had a harmonic drive on a brushless pancake motor, giant NPC 555 motor, microcontroller, force torque sensors, accelerometers, whisker sensors, everything in the kitchen sink was on this. This one cost about $3,000 a piece, and it could dock automatically and all that kind of stuff. The interesting thing about this was we did, I think, 3 demos with this and then stopped. This thing, we did hundreds of demos. And why was that? It was in part because this was a bear to work with. We had this real-time operating system, wind reverse systems. It was really complex. It was hard to use. This thing was super simple to do. We couldn't do as much. It didn't have as many sensors or capabilities, but we could do simple things with it. And so we did, and we did a lot of them, which is interesting. So there is a tendency when you design systems in general, but modular robotics, that's a thing we call feature creep. It's easy to think of things like, in this case, what we did was, if we added a force sensor on this thing, everything would have a force sensor. We could sense the force along the whole arm. Wouldn't that be cool? Let's add a force sensor. Oh, if we had an accelerometer on every module, we could see what the direction of each thing is. Oh, that was really cool. So we'd add it. And then we'd add another thing, and then we'd add another thing. And pretty soon, you've got this giant thing that's got too much. So these guys at Carnegie Mellon, in the Claytronics group, they come up with this thing they call the ensemble axiom. You should only put in what you minimally need and don't add anything else. So their mission was to make modules, reconfigurable modules, as small as possible. They wanted to make these little nanoscale modules. This is one example. This is about a 4 centimeter. They're called Atom, which was electromagnetic cylinders that roll around each other. They did make one that was about 2 millimeters. That was a cylinder that could roll around with external actuation. It wasn't much more than that, just a cylinder. No smarts or anything on it. So they were, essentially also trying to look at shrinking things down. And so essentially, shrinking things is hard. Miniaturization is hard. The last thing I want to talk about in terms of miniaturization is microscopic robots. So there are actually, you can do things on the microscopic scale. You want to have a robot on the microscopic scale. Ideally, you want to have these components. Computation, that was essentially solved, microscopic computation solved, with VLSI years ago, decades ago. MEMS structures allowed us to make structures that are on the microscale also decades ago. Actuators are also, we were able to make actuators very, very small. So it used to be that, okay, how can we miniaturize actuators, but that was like, you can't make motors small, but there are different types of actuators that you can miniaturize. Then the real problem was, how do you get power to them? How can you have power transmission? And that's one of the things that Mark Miskin solved while he was at Cornell, which was this. So this is a robot. This is powered by electrochemical action with sunlight. It's light powered. It's not a huge amount of light. It's just like room light or solar light. Basically, there's a little laser beam that gets this thing to walk. This one doesn't have any computation on them. But I'm working with him and David Blau at University of Michigan to put microprocessors on these systems so that the thing is it has to be very, very low power because it's just being powered by light. And that's kind of the tricky thing. So we got that. We've got low power computation, low power actuators in the structure that can actually walk or move around in an environment. The thing that is I found surprisingly difficult is the sensors. Sensors is now the thing that is very difficult to put on the side. Part of the thing is with the microprocessor that we were able to put on these systems, the amount of memory that we could put on there when you have this low power system is tiny. The first system was 100 bytes, not 100 megabytes for people who are used to computers where you've got gigabytes of memory. 100 bytes. I think the new system will have like 1,000 bytes. If you think about sensor processing, you're used to using point clouds and GPUs to process things. Well, 100 bytes, I mean, you can't even put a bootloader in 100 bytes. You can't put an operating system with 100 bytes. What can you do with 100 bytes? Not a lot. So it's interesting. The problem that you might say, everyone in the roboticist, I'm used to thinking about, miniaturization of CPUs and all that stuff is easy, kind of, but when you're at this scale, with this power, the interesting problems are what can you do with very, very resource restricted memory and the sensor. You can put like temperature sensors, you can put pH sensors, you can put sensors that sense different properties of the area, but range sensors are very difficult. And that's the thing that I think every mobile robot has these days that you have moving around. So an interesting thing that if someone could come up with a miniaturized low power range sensor, that would be super useful. I don't know how to do it, but that could be the next step. Okay, so that's miniaturization. I think, maybe we're getting towards, I don't know, it's hard getting to the T1000. Next issue is strength. So one of the things with modules that we characterize them is something that we call characteristic strength. That is, as you put modules end to end, how many can you extend in a cantilever fashion that can support its own weight? And usually, there's this square cube property where the actuation strength goes by the square, but the mass goes up by the cube. Therefore, it gets harder and harder to go on, especially when you're cantilevered. The torque is, not quite quadratic, but something like that. It goes more than linear. So it turns out that for our old systems, the old polybot systems, this one had a characteristic strength of about 3. We only put about 3 modules that it could lift. This one, the G1V3, where we had a harmonic drive, we put everything in there to make it as strong as possible. It still only had a characteristic strength of about 8. It could only hold about 8 of its own weight. So that kind of thing really limits what you can do in terms of having a system. You can't have a system that's really big by extending a single arm because it can't lift its arms alone. So one thing that you may think about is that you could do things in parallel. So part of the thing is if you look at animals, it's kind of interesting. You look at a flea, the jumping height of a flea is about 200 centimeters. The jumping height of a horse is about 100 centimeters. That's roughly the same order of magnitude in jumping height, even though the mass is 6 order of magnitudes different. So the jumping height is basically the same for animals. And that's probably because the muscle's force is proportional to the cross-sectional area. It's L squared versus cube. But part of what they do with muscles is if you need to be stronger, you put more in parallel. So can we do that with modules? Theoretically, you could attach a module to a joint, and if you wanted more strength, you could maybe add another module. You could add another module along the axis, and you can double the strength, or just keep adding them along the axis. But you can't put them elsewhere. If you put one here, maybe it could help for a little bit. If you put multiple ones, stacked together, then you could kind of help it move a little bit. But it's not the same as, because the joint axis is different, you can't just add them. Here you can add them linearly. It's not L squared, it's just L. It's just linear with the number of modules that you add and keep the strength. which is unfortunate. So we can't really easily put them in parallel in the way that you would with muscles. Also, it's intuitively, you can think of, if you want to lift this table, if it's really heavy, you get 2 people. If it's even more heavy, you get 5 people, and everyone kind of lift in parallel. But that's because the kinematics are in such a way that they're not constrained, whereas here, every time you get a module, kinematics are constrained by how you put them together. So one interesting thing we can do, if we put things in parallel is exploit the singularities. So what's happening here is there's a loop and there's a ratchet system on each module. And what's happening is it goes to singularity. When you're in a singularity, you have very large mechanical advantage. So you move one end into a singularity, get this, it's lifting a weight here. That's, I think it's like a kilogram or something. And it's 6 months, it's already at its limit if it was just a characteristic string. But because it's using part of it that would lock one half, it's a loop. So it locks one half, gets the other half to move through a singularity, to add that part to move up, lock this one, move this one to a singularity, move that up. And so by process of ratcheting, you can lift very large forces. So that's one way to exploit kind of a parallel loop mechanism. The other thing so this is unpublished work, but I think something I'm pretty excited about how we can actually get scalable revolute joints. So with, one thing you might, not only is the actuation a problem, but the structure itself is a problem. If you look at the hinge in a flip phone, you could theoretically take a bunch of flip phones and attach them together and have a much stronger hinge, linearly by how strong it is, but you couldn't, let's say, make a bunch of cell phones, put them together with the size of a car door and have it be as strong as a car door because the diameter of the hinge is just too small. It's not strong enough. It's just linearly increasing the length and not making it stronger in its diameter. So one thing we can do, we can use, basically it's a scissor mechanism. So the critical thing here to notice is that the axle is virtual. And what you can do here is you can add more layers to this scissor mechanism, and the strength of the scissor mechanism is much stronger because we have so many more joints. And there's the kinematics are not constrained, there's a virtual hinge instead. You can take that same process and extend it out this way as well. So not only higher, you can extend it out this way. You can take each layer and extend it out this way. It's 3-dimensional. You can extend in 3 dimensions instead of just 1. So now you have a way that scales actually even better than muscles, which are squared. It's actually cubed in terms of the way the strength increases in the joint. If you add a motor at every joint, you've also now scaled the actuation much better than you can with motors. So really, one of the exciting things also that we kind of theorized, this is all unpublished, and we haven't actually finished doing the experimental work on this yet. But the theory says that if we can buy these little motors, like almost like pager motors, but there's this one company in China now with the tariffs, it's a little bit more expensive, but you can buy these little motors, and by our calculations, you take 100 of them, and you put them together in this type of system, it can be faster, stronger in terms of higher maximum torque, lower costs than an equivalent large motor that you might use for a humanoid or a robot dog. We've done the comparison with a T-motor, and it's just better in all aspects. The one aspect it's not better than is in volume. You have all of these distributed motors, it takes up much larger space, but it's lighter, faster, stronger. And the reason I think that it's better is because thermal characteristics. With a typical T-motor, you cannot run it at stall. If you run it at stall, you'll burn up the coils because you can't dissipate the heat. If you got 100 of these guys that are all spread out, thermal dissipation is many times better, and so you're able to actually run it at stall, so the max torque is much better. And so I think it's super exciting. It's a much different way to think about actuation, which in the modular sense, where you want to be able to grow the system by adding things, it enables a lot. So we're very excited about that. Okay, so another thing about size and strength is something we call the variable topology truss. So this is is kind of the opposite of miniaturization. This is big. This is very big. Part of the problem here was that the Air Force was looking at, can we have a system that could support a damaged building? So we need the system to be as big as a building and be strong enough to hold it up. And so this is one way that can do it. Trusses are essentially stronger than materially efficient. The reason that we have cranes that are made of trusses and we have bridges, the interior of buildings are made out of trusses is because it's materially much more efficient. This is the node of the truss that shows that it's reconfigurable in the sense that you can add multiple truss elements to the node and increase the degree of the node, again, because we have this virtual axis in the center. So we can do reconfiguration with them. I think earlier you saw these are prismatic joints, something we call the spiral zipper, which have a very high ratio expansion ratio. So we can form lots of different shapes, various topologies. So here the students are putting together a bunch of tetrahedron or other shapes. We can do lots of different things with it. Another kind of fun thing we can do is path planning is a little bit different when you have a robot that can change its size. Obstacles, you know, you can become really tiny if you can change your size, which is kind of useful. It's kind of a fun little thing we can do. This is a video of the robot growing in size. It's going to essentially go up to reach the ceiling. One problem was the students actually put the wrong band here. They put a shorter band than they were supposed to, so collapses somewhat dramatically. This is we have a metal version that's spring steel. So that's what we would use to be super strong and support a ton. But that would be super dangerous if you got this kind of spring steel flaying around basically like a sharp knife. That's great. So we use the plastic one in general. For reconfiguration, one of the things we've discovered just recently, we just published this, it's much easier to reconfigure in 2D than in 3D. So we're able to have the system, they're just the prismatic joints that can move. If you can get them to move in the plane and then dock, I don't have a video of the docking, but there's a way that the elements can dock together. You can form larger structures. In this case, it's formed the flattened shape of a tetrahedron. Once you're in a tetrahedron, the problem is you're in a singularity because you're all flat. But if you can exploit environmental features to get yourself out of that singularity. So in this particular case, if you find a little hill, you crawl over the hill, the node is lifted up high enough out of the singularity so then you can pass up, now you've got a 3D structure. So that's reconfigurability. What are the issues with reconfigurability? This is the thing that primarily distinguishes self-reconfigurable systems from other systems. Let's see, how are we doing on time?
We have another half hour.
Half hour?
Yeah,
all right.
we can have. Yeah.
Okay, all right. So the main thing is the ability to attach and detach. That's what we're adding. And to detach, you just basically fall apart. So that's relatively easy. To attach, there are 3 steps of docking. You have to approach, you have to do, usually there's some precision required to get the things close enough so that you actually make. That's where there's something we call this open loop guided motion within what we call an area of acceptance. So that's the thing that a lot of groups try to work on for their modular reconfigurable docking systems. You want to have a large area of acceptance. So let me just give some examples. For the DARPA temp system, it has this kind of hook and loop system. So one module will stick out a string in a loop, and then a hook will come out and grab that loop and pull it in together. Here you can see, yeah, there's the hook grabbing that string. This graph here shows how we mapped out what that area of acceptance is. So the area of acceptance is basically 3 centimeters out in terms of what it can reach. It can hold about 40 newtons and takes up about 5% of the volume. This is another system. This is so the Polybot V2 system. There was a kind of a what do we call this? A little nub thing that sticks out and goes into a hole. where there's a hook that grabs onto the groove. That's actuated by a shape memory alloy. So they're all chamfered, which helps a little bit in terms of a peg and hole type situation, but not a lot. It's only about a 3 millimeter error that it can compensate for. And it's a relatively low profile, all within the width of this end plate. I had one of my students work on coming up with increasing that area of acceptance. So here's a system that has basically 100% of the size of the face, essentially, and with a large errors in angle as well. It kind of automatically aligns if you have two systems that are approached together. The SMORE system is interesting. It uses an electropermanent magnet, not an electromagnet. So I'll talk a little bit more about that. It can hold about 50 newtons and deal with errors up to 7 millimeters. It's very fast. And it's also low profile. So this is a system by Henrik Lund and David Christensen and Kasper Stoy called Atron, which is pretty old. But this is the system that I saw had the best latching mechanism of any self-reconfigurable robot. It would attach it can attach 8 modules to each one. It has basically hooks that come out and grab onto this bar. So it's very strong. It can hold something like 800 newtons. Very, very strong. It could have a pretty good range of motion to grab on. But the thing was, about half of the volume of the module was the latching mechanism. So you had to dedicate most of the module to this grabbing system in order for this to be alive. Of course, they had 8 of them as well. But in a self-reconfiguring system, where self-reconfiguration is the main thing, that may be okay. It can't really do much else in terms of it has 1 degree of freedom for rotating. Okay, so this is the electropermanent magnet, something we call the EP face. Just to give you an example. The way it works is it has magnets with coils on them. You pulse a high current through the coils enough to flip one set of magnets. So essentially what that'll do is it'll turn the magnets on, or you can pulse it in the opposite polarity and it'll turn the magnets off. So here you can see the different relative errors that it can still pull itself together. Another thing for self-reconfiguration is that the profile is very very low profile, and you can do this kind of sliding motion, which allows it helps a lot with self-collision, which is the main issue with planning for these types of systems. So how many people have heard of or know how to use electropermanent magnets? A couple, good. Okay, pretty good. So that's good. It used to be that I would talk to people and they've never heard of electropermanent magnets. They always think electromagnets. But this is the kind of cool technology that I think, I'm not going to go into detail because we don't have time, but if you're interested, talk to these people, because it's really cool. The fact that you can turn a magnet on and turn it off with just a pulse and not have to keep wasting all that electricity is very enabling. Another interesting thing that we can do with latching systems, so one of the problems with the DARPA 10 project was that we had to survive what was called sea state 3. Sea state 3 is the amount of waves in the ocean. And if you have a large structure like this, in sea state 3, if it was rigid, the forces on the robot are huge. You would basically need to have like a 6-inch steel rod going through these things to support the moments that from the buoyant forces. So a better way to deal with that is, instead of having a rigid object, is to comply. Have the robot just comply with the wave, and then you're okay. And we can do that because we have string-based latching. So we just let the string out a little bit, comply, and then when we need to be flat, you can bring them together. So for example, if we were a landing strip and you had an airplane that was going to land on this structure, you'd want that place where the airplane was touching to be flat, so you could theoretically have that flat part right underneath the wheels as it's landing. We never demonstrated, but I think it would have been really cool if we could do it. Okay, so I'm just going to say one thing real quick about reconfiguration algorithms. The primary thing with reconfiguration algorithms is self-collision. I didn't allow for me to realize, but like here, this is Kasper Stoy's work from a long time ago, showing a bunch of modules that it's a fictional system, but it's essentially a cube that can move along next to each other. The way he got it to work is to have the target structure be porous. There's lots of areas for modules to move. don't have that, it becomes very difficult to do the reconfiguration. These guys, we came up with primitives that they can work, but it's because the modules can compress and be smaller within themselves to move around. For even the truss systems, self-reconfiguring VTT, self-collision of these rods is something that is difficult. And so we have a couple tools using knot theory and the topology of these types of systems that aids in terms of trying to figure out when will you have collision, self-collision or not, which is interesting. I didn't know. Anyway, so we have a variety of papers on that. Last thing I want to talk about with self-reconfiguration is an interesting problem that I think I'm finally being able to start to address, tackling this one problem, which is if you have a modular robot system that can have lots of different shapes, how do you choose what shape it should be? If you have, and that's based on the task. If you've got some tasks, you want to do some type of assembly, what is the right shape? So I know a lot of people think these days, humanoids. Humans can do anything, so it should be a humanoid shape. I think that's probably not true. The optimal shape, who knows what it could be, but I think I have a way of starting to address that problem, which is if you start with the task. So if you have a basic task, like here's an example we have just made a proposal. Let's say you want to deliver a first aid kit to someone and it's in an environment like a forest. So you can ask like a VLM system, what would be a good robot system? It can look at the environment, potentially say, okay, for this type of environment, these are the types of robots that might work well. Based on the geometry of the environment, maybe you know what types of motions, like it says a dog, you know, okay, the length needs to be this big, you can make it this big, that big like a payload, and then sources you need to do. You can do what we call morphokinetics, generate kinematics, that will give these types of motions for each leg. You can do the distribution of what actually it should be and all this kind of stuff, and then you can put together a robot. You can simulate and validate that system and then iterate through to see if it actually works. I think that's what I think is the future of where we're going with this system. And this is a figure for a proposal that we just submitted with the government shutdown. Everything stopped, and we were supposed to hear about this a couple weeks ago. Of course, we didn't. I'm not going to say we won't win for that, but hopefully we'll win and get that. So essentially, this new project that we're working on uses this parallel actuation. We're going to use first machine learning, blah, blah, blah. There's about a dozen professors involved in this proposal for control. The key difference between this and all the previous work is that we're doing fine-grained modules. So all the modules that I showed you before had computation, motors, actuators, sensors all together on a single system. And because of that, it was super inefficient. Because of that, everything it did was useless. Couldn't do anything useful because it was so inefficient. It barely lifted the arm up. If we have some things where we don't necessarily have to have a module, a motor at every place, we can have structures that are parallel, we can grow things, we can distribute sensors where we need them, we can be much more efficient and hopefully start to do useful things. Okay, that's the end of the modular robotics part. Shoot, I took up too much time. Any questions on modular robots? Yeah.
Yeah, fascinating talk. I have a question about the energy efficiency or the energy consumption. You have any general comments for reconfigurable robots?
So for energy efficiency in general, these systems are inefficient in general for the modular robot systems because they have all this redundancy, motors everywhere, computers everywhere. Theoretically, you could shut them down, but they're still there. They're heavy. Usually, if you want things to be light if possible, if you want to save energy. That's where I think if you are able to do things in a fine-grained scale, you can make things lighter where they need to be. You can be more efficient. Hopefully, they'll be more energy efficient. Yeah.
I think most of the robots are like kind of rigid. So are you guys thinking of like moving on to like soft robot instead of the rigid?
Yes. So actually, this part and part of this proposal was hybrid, mixed, soft and hard. So these links, some of them, depending on what we need, can be soft or hard. This was a giant proposal, So we had everything: soft, hard, distributed, centralized, machine learning. Yeah.
I wonder if you have any thoughts on how do you start to think about when does the composition actually become more than its parts, right? Like, especially if you're thinking about heterogeneous components, like when can we actually say that, or do we think that we could get a system with this modularity that becomes more than its
So I guess what does it mean to be more than its components? And certainly a system that's put together will be able to do more than the individual components by themselves.
I guess maybe like thinking about like the maybe specifically with computation, like the benefits of distributing the computation instead of centralizing it. I think it's maybe one.
Okay, so for distributed computation, there are aspects of efficiency and robustness. You may have parts where the hand can do localized computation for sensing and actuation because it's all local and doesn't need to go further than that. And so it doesn't need to communicate up to the brain, it can just communicate. So it could theoretically be faster, maybe not use as much information, and so that can help. In terms of robustness, if the hand breaks and, like Iron Giant can roll off by itself to do whatever it needs before it comes back, theoretically it could be more robust. I want to go to the robust innovation just because we don't have time, but we can get back to that. We'll have lots of time for questions afterwards. Just so responsible innovation, these are kind of the principles. These are what we're thinking about for responsible innovation. We want to be able to potentially foresee impacts, both positive and negative. We want to be able to reflect on what assumptions we made as we went. We want to be inclusive. We want to think about diverse stakeholders. We want to, this is how do we involve the public? How do we involve policymakers, decision making, and then being willing to change course. This is the kind of thing that I think, when the dean asked me to start up this effort, I said, we're engineers, we're not good at this. This is, sociologists, lawyers, maybe that's policymakers. That's really their area, but it's important. I think it's important for us to start to think about what we can do and what I'm hoping we can do, and I'm hoping especially the educators here can help me think about these different types of things we can do. We can educate the students. So one of the things we're afraid of is that PhD students, researchers, people who are doing research, you go blindly forward in whatever you're doing without necessarily thinking about the impact. There's the quote, you were so excited by what you could do, you never thought about whether you should do, that kind of thing. How do we support research? Can we help researchers to think about things, to teach other people, and that kind of stuff? Can we educate the lay people? A lot of times, some of the issues with lay people is that they don't understand the problem. Like especially with AI, they don't understand AI, and so they're super afraid of it. They don't understand humanoid robots, so they're afraid of them. And so educating them is a big thing. So what I've been doing for the education part with research students is asking 3 questions. What happens if we succeed in making something useful? What could go wrong if we succeed? And how can we mitigate that? So for my problem with the modular robots, what happens? There are all kinds of areas. Every department has different types of things that could go wrong. Microplastic solutions, climate impacts, all these kinds of things. And what can we do about it? So this is a video that I made in 2008. That was it was I asked ChatGPT. It said it was in 2008 there weren't that many YouTube videos and not that many people. So I asked ChatGPT to say what would be the equivalent views if I had 1.4 million. And it said, well, it's equivalent to 130 million people. So what happens is there's a robot is walking along. My student kicks it. So we call it self-reassembly after explosion. It falls apart. Each one of these little modules detects it has an accelerometer on it, it detects that it's fallen over, it rights itself, goes into a search pattern. They have a smart camera on board, which is unusual at the time. Phone cameras weren't that popular. And the blinking LED is actually a communication method. So they do a search pattern and then they dock together and they continue moving. So if you look at the types of things that people commented, you know, there are things like, there are things like, oh no, it's, you know, it's, there are people that are, you know, it's C1000, it's Terminator 2, it's never going to, you can't kill it, it's, you know, that kind of thing, which is silly and a little bit ridiculous, a little bit untrue. Okay, so what happens if we succeed? For our system, we have a self-reconfigurable robot. So, okay, the exercise I want to, when I asked, actually I had lunch with some of the PhD students here, the exercise I asked them to go through is, think about your research. Think about your research and imagine that research is wildly successful. So we talk about the ChatGPT moment. ChatGPT moment is, you know, when ChatGPT suddenly was super successful. It was like, oh, actually people recognize it's used. Everybody's using it. It's big. So what is your ChatGPT moment? What in your research, you're doing something and it becomes more successful than you ever imagined. Everybody's using it. What does that look like? What is it? So first talk about that. And then, so in my case, it's okay, you have this robot that's super useful, the artificial general intelligence, it's the artificial general intelligence, but artificial general intelligence for robotics, it can do anything. But what could go wrong? So what could go wrong if it's actually successful? And that's the type of thing that's difficult, because you have to think past what you're aiming for. You're aiming for something good, but what could go bad? And usually we don't stop to think about what could go bad, but we should. We should take a second to step back and think about what could go badly. So at lunch, one of the students talked about this interesting probing device to sense. You could actually sense whether there's a tumor or not in tissue with a force sensor. And so we said, okay, well, what if this leads to the cure for cancer? You cured cancer. Wow, that's huge. What could go bad? And another student said, oh, well, actually, I don't remember if he's here. What did you, do anyone remember what he said? Basically,
some company only use that for certain person.
Yeah, what if a company gatekeeps that? They discovered it and they said, okay, we're only going to allow certain people to be cured of cancer and everybody else with cancer has to die. That's terrible. You know, that could start to have social unrest or other things. There are impacts that you don't necessarily think about. So let's do that for a second. Does anyone want to talk about, I just want to open this up a little bit. Anyone have any ideas about that? Yeah, Laura.
I'm going to bring up an example that came from a time I did something on an editorial, so associate editor side of things that kind of speaks to this, which is sometimes when things seem like successes, but there's actual unintended like societal cost here. And it was some robotic system to like interpret sign language or like make a robot hand do sign language. And one of the reviews I got back, luckily I had the luck of sending it to a person who actually knew what they were talking about, said that here's a set of 3 or 4 articles that say that the community that you are trying to help doesn't want the device you're building. I think that that's a really interesting thing to talk about in this regard. Like, should we still build things if the current people right now don't want us to build them? I would kind of do not know, but you know, there may be questions about others on that.
Yeah, that's, so in general, for research in general, making sure that you're doing something that's correct for the target audience is huge. Yeah.
A counter argument to that would be, what if those people don't know what's good for them? And maybe they really need this and they just don't know that they actually need this tool and it could be very, very helpful.
Yeah, that's true. So the prosthetic hands is an example of that. I've heard that, I was looking at prosthetic hands for a while, and when I talked to people, they said, you talk to people who need a prosthetic hand, this is 30 years ago, they don't want a hook. They don't want something functional that you can actually pick. They want something that looks like a hand. They'd rather have something that looks like a hand than something functional because they're more worried about the social impact. That's changed now. Now, especially with all the soldiers who've been damaged or hurt and have amputations, black hook hand, that's really cool. You know, you got this whatever thing. Look, I can turn it into a knife. You know, it's different. So times change. So maybe that counter argument works.
Yeah, if one day we build human robots to be super realistic, just like humans, maybe some people may be more willing to interact with humanoids instead of real humans.
Yes.
So that could cause issues like isolation.
Oh, that's happening now. That's happening now with AI. There's all kinds of social impacts of the realistic, people are chatting with chatbots that are more real, and then, you know, there's the incident where a teenager killed himself, in large part because of the interaction with the AI. Maybe it's worse for humanoid robots as well. Let's, so, yeah, did you?
Yeah, I guess I don't know, because I can listen to a seminar from Whitney, it's like the development, and they've been talking something about agentic research. Right now, people are just crazy about agents, and because you can generate most of like research work, like coding and programming, managing data. And I just feel like if large company can manage that, let's say, be the owner of these agents tools, it's going to be a conflict with the existing workforce because unemployment going to be expected.
Yeah, so that's the problem. Impact on the workforce is a common thing when we talk about robotics, successful robots. So this is one of, so there are a couple things that are common. Now, this is a scene from WALL-E. I don't know if you guys remember how many of you have seen this, but basically over-reliance on technology, like if robots do everything for you, if I was successful, then you end up with people, because at the end of the movie, people just become blobs. Like they can't even walk, everything is interacting through visual stuff, they lose their sense of their own agency, culture stagnates, they lose their connection with nature. So yeah, bad things can happen. There's there basically one other major thing that I think, as I've done this several times with students talking about different aspects of robotics research. And I think the thing that often comes up and applies to most of the projects is security. Security is always a concern in one of two ways, or sometimes both. If you have any powerful technology, what happens if a bad actor takes control? You've got this robot, like in my case, a robot that can do anything, whatever. Someone takes over your home robot that's your butler. Now it can do anything, you know, controls your house. It can steal from you. It can do whatever bad things it wants. That's bad. That's always a word. Security is something that, especially if you have a powerful technology, it can be used against you. So you need to somehow think about security. How can we get that in? The other thing is that if there's any kind of transmission, a lot of these robotic systems have information technology built into it, communications mechanisms, and so privacy is a concern as well. And that's true for very many robotic systems. I know we're short on time, so just want to, so these are basically the things that we talked about. How can we how can we educate our students? How can we educate the general populace that can then affect policymakers so that we can actually make the right decisions? And this is another scene from Jurassic Park. You know, you scientists were so preoccupied with whether or not they never stop to think if they should. And so it's Jeff Goldblum anyway. This is, you know, Jurassic Park, you're making dinosaurs that kill people, and all this typical bad things. All right, so one last thing. I do have an NSF contract that's, and they've been asking me to also think about innovation. NSF, innovation and entrepreneurship is a part of, large part of innovation And so that has a ton of different ways that it can help in terms of helping people do entrepreneurship and funding. So that I'm just showing this up here as a reference. There are a lot of different things you can look at. These are all the students that have been involved in all these different projects from over the years. AFOSR, NSF, and DARPA have also been responsible. So yeah, if you need to go, I know some people are leaving. I'll let you leave, but if you can stick around and talk, I'd love to see you. Thanks.
Yeah, thank Lee for a great talk. So I guess we can do like this. We still, have a few questions here before we officially end. And then, people, if you have other things, you can go ahead. But if you're interested, you can remain here, for the discussion for the next half an hour, for example. Yeah, we can take a few quick questions if you guys have questions. Yeah.
So a quick question about, I'm looking to about the reconfigurable robots and, bigger, so smaller is more expensive. And also not perform good. So my question is, what is the underlying mechanism stopping or serving as a major obstacle for human beings develop this kind of technique? So I have been thinking about, more like we have a lot of modules, and then when these modules exceed a certain large amount, and then by design algorithm for them to cooperate with each other, it's more like the emergence. So it is because human beings have so little knowledge about emergence. It's more like the high-level intelligence from the low-level property techniques. That might be the major problem or shortcoming or limit in the fundamental mechanism, or what I don't want to get in your thoughts.
Oh yeah, no, that's a great point. That's so super interesting. If we can develop a system, maybe this gets to Laura's question about the sum of the parts. If you can get smaller systems that can put themselves together and then do things in an intelligent way that is better than you could have put them together manually, then we gain something. So when did that happen? I don't know. One kind of side comment. I work with architects, and they talk about emergent behavior. These are designers, typically. I don't like the term emergent behavior because they think, oh, we have this algorithm and it creates this fancy curve that I didn't quite correct, and it's super cool because it's emergent. From an engineering point of view, I always think of emergent as being something that you did not program, something you did not intend. You've got your car, it breaks down, emergent behavior. You did not intend that to happen. If you have a system that can build itself and do something better, we want that to happen. So it's not emergent, it's just, we didn't understand it all that. So that's the only thing if we can do that, that would be amazing.
I think maybe because, we still don't know what caused the emergence. More like why this kind of high-level intelligence, how they come from a low-level operating systems. And you said, this kind of things should not be programmed because we don't know how to program it.
So yeah, I mean, the same thing is true with like ChatGPT. It's hallucinating. That's emergent. But even then, all the answers of ChatGPT is this big black box that's got too many billion of parameters, and then we can't understand it. But it is what we want it to do, except when it gets things wrong. But so I don't. Yeah, that's. When can we get that moment where we've got this small thing that does more than what we understand? That would be amazing.
I guess kind of more of a comment. I don't know if there's an answer to it, but it feels like with any sort of paradigm shifting technology, that eventually there will be unforeseen problems that are kind of happening. Like if you look at Facebook, for instance, they make it it's going to be setting up parties and keeping track of your friends, and then the Arab Spring happens, or with electricity when it first came up, people didn't realize that they would update fire codes. So I feel like that's kind of the question is there a point where the technology is so paradigm shifting that it could be catastrophic, such an error?
Yeah, no, those are great examples. I think so with fire codes. At first it's a problem, and then we have policies to fix those. I think the main thing is we need to be open to those changes. Being closed to them ends up like Facebook. I've heard that some of the engineers knew that the social problems might happen, the splitting up of the country because of the way the algorithms work might happen. And they didn't, or at least the company, and they still, I'm not sure they're doing anything about it. They know it, and it's a problem. But so we need to have people that are ready to fix things when these bad things happen. Did you want it?
No, I think I must have been like moving my hand or something, but not to raise a question.
Okay.
I wanted to ask you, this is on the responsible or innovation side, but you have that slide of, what can we do or what should we do, and educating, talking to students about it, and thinking about different ways to sort of try to guard against irresponsible innovation. But one of the things that I was curious if you thought about is the role that kind of our current incentive structures play in driving this behavior. As an example, in academics, there's an incentive to build the potentially not as useful but cool-looking robot. There's the incentive to get the 1 million, 100 million likes and have the viral video these days. I think even university institutions are pushing their faculty to have those viral moments because that brings attention to the institution. And so I see, in so many regards, all of the incentive structures driving people to focus only on the positives and cool and exciting and hyped. And it's not as fun and not as cool to be the responsible one saying, but should we not do that? If you can comment on that.
Oh, that's great. That's really important. Actually, I had this slide. Academia is run by citation, which is not necessarily good because you do the cool thing, people will cite you because everyone they know that if you don't, the other reviewers have seen it on YouTube, so or whatever. And is that good? It's not. I don't know. That's good. Archive is now the way it's becoming good. It's not even peer reviewed, but it's going to social media first and then getting out there. What happens with that? How do we get people to be more responsible? I don't know.
Just along those lines, I do think there are some small case studies where communities have decided that things are verboten, right? Like human cloning. And then when people do some of this stuff, they might get press, but typically that press shades much more in a negative direction. Like they're not going to get the citations, no one's going to cite their work.
Because of the negative side.
Because of the negative side, but that takes a community sort of thinking ahead of time, where they're seeing where they're heading and deciding to make a change.
Yeah.
How do you see kind of the interaction between researchers and the people that they're testing their products on consent changing? When I think of self-driving, a lot of that was tested and beta tested on the streets, and as a pedestrian, you're now basically being collected as data and put at risk with these new systems in order to improve them with a product that might not be fully functional and you could die because of it. Again, and in addition to that, things like ChatGPT, a lot of artists have their work basically taken to create AI-generated art. So they're essentially their work is being used to sell as a business. How do you see that, I guess, going forward in terms of responsible design?
Yeah, those are issues. I don't have good answers. So these are, I think a lot of people recognize that these are not good, and there are better ways to do things. How do we get people to do things better? I don't know.
Great. Yeah, I think this is a very engaging, interactive seminar here. Thank you so much, Dr. Yin. I guess the room here is reserved 4:30, so I guess maybe many people still have questions. Please feel free to stay here and have a conversation with our speaker here. And yeah, let's just officially end our seminar here. Let's give our applause. So for all faculty, can I just request you go to the front? We want to take a picture together. All the faculty member, yeah. Maybe you